afternoon, and in today's recording, we'll be demonstrating my knowledge of creating a aerofoil in Ansys using the software available. I have previously recorded and made a NACA 0012 biplane configuration, and the dimensions of the biplane are off of the Gene Sport biplane, which is required to be built by Task 1 and compared to Task 2. I have done this because my PC's limitations plus the recording time of my recording software would exceed each other, so I cannot record for long enough to show all the relevant information live. So you would start by importing your nodes, which are done by going onto airfoil.com and then taking the nodes off, and taking the nodes into a Excel document once you have applied the correct chord for the aircraft. And the chord for our aircraft, our aerofoil, is 914.4 millimeters. Once you get the information, it comes in a file from Excel, like this, and then it gives you this information as base. Then you add 1, and then you add this for the number of nodes for your aircraft. That can vary depending on the aerofoil. Then you copy and paste the aerofoils, each individual coordinates for each node here, and you put the number 0 there. And then from there you would take this into a notes document, because you cannot directly take a Excel document into Ansys. You may be noticing this is not labelled as the NACA 0012, as I'm using for the rest of this. This is the Clark Z aerofoil, which I'm using for my task 3. I'm using it because it is the data I have available at this time, most conveniently. Once the nodes have been imported into Ansys, you can then use the Concepts tool to create a 3D curve. And you would then go onto a 3D curve, and you would select Draw from Nodes, and you would join up all of the nodes from the top tail all the way around to the bottom tail node, and then you would accept, and then you would draw a line between the two nodes to seal off the aerofoil and make it a complete shape instead of leaving a gap, as it would if you were just using a 3D curve. Once this has been done, you can create a projection in a separate plane, where you can then take your 3D curve and copy it into a sketch, which you can edit to create your aerofoil as you would like. From here, I would then build a base. I would build a base off of here, which is completely straight up here. The number of millimeters required for the aerofoil. I just have the notes here for the exact integer. You would create it with an offset of 874.268 millimeters horizontal, and then, my apologies, I mean vertical, and a horizontal offset of 438.15 millimeters. And that would give you an aerofoil with your second node placed here. Then you can go into the sketching tool. You can go to modify, and then you can copy, and then you would be, as this would be a sketch, it is now usable, it is now copyable, and it is now editable. So you can copy this piece here, and this piece here, which is a very small little conjoining piece, which conjoins the two aerofoils together. You can copy those, and then you can paste it, and the node will lock onto the nodes described by the drawing of the horizontal and vertical offset. And then you can delete those construction lines, scaffolding if you will, and it would give you aerofoils in this configuration here. Then you would draw a box around it to simulate the environment, of course. Preferably, it has to be at least 10 times the chord of the aircraft, which has been done as part of my report. And then I like to use a ratio of 1 to 5, so it's quite long, but this would very well represent any turbulent air coming off of the back of this aerofoil. Once this has been done, you can then take a surface sketch. A surface from sketch, and then add these as your part body, and then it would create what we have here. And this here is a aerofoil config. No, two aerofoils in a environment which is now ready for meshing, which is I have saved here. So using this, now when you've brought it into this tool, personally, my preference is to straight away mesh. However, this is a complete model. This is not what it would look like at the start. Straight away, I would mesh, and then to around 0.1 meters, as has been done here as part of my other task. Then I would refine, and we do it like this. Insert, and then it says refinement. I would select that, then take it to 3, and then once the mesh itself has been refined, I would edge size each of these aerofoils to more accurately depict each aerofoil, including the curves such as the radius that I have on the end of here. Once this has been done, you could then refine it. As you can see here, I refined it 3 more times to provide an extremely accurate mesh for the best possible results for this task. After doing this, my personal preference is to label the named sections. Some people prefer to do it before, however, I like to do it at the end, just before going to the analysis. As you can see, there is the inlet, the outlet over here, this sim, which is these two. Then there is of course, the bottom and the top aerofoils, which are displayed here. Now, moving on to the research. This is the data I've already gathered, so I don't have to run it again with you. Yeah. However, I may, if time allows. So, when you come onto this screen, first, actually, as a side note, I'll just mention all of this information is controlled through this screen here. Of course, you know this. I'm just demonstrating what I do too. You would go from the geometry to the mesh to the setup, and the solution and the results are all available from this software, so there is no need to change. You would edit a bunch of the different values, some of which I'm so sorry. Some of which are the reference values, which are found here. So reference values, most of these will come as standard from most of these will come as standard just by loading this into the software. However, I have edited the length down to the chord of the aircraft. No, of the aerofoil, sorry. I have edited the velocity to meters per second, and I have I have changed the reference zone to the surface body. Something else that I've added 2 report definitions. One for the lift coefficient of this aerofoil, and one for the drag coefficient of this aerofoil. I will make a new one. I will make a new coefficient to demonstrate my knowledge of this. You would open up this, which would bring you onto the drag report definition, and I would relabel this as drag, as I will do now. then I would select the bottom and the top aerofoil to be tested upon. Then you go down here and you need to select these three: report file, report plot, and print to console. Then you would press OK, and that would show you the lift coefficient of the simulation. However, I have already done this for the one, so I will be pressing cancel here. And you would do the same again for lift and drag. The airflow can't be laminar because then it would not be testing it very well. So you would go into here and edit it from its default laminar position to, I'm not 100% sure how to pronounce that. However, you take it off of the norm and you add some turbulence to the airflow to provide more accurate data to a normal flight. Press OK here. Some other things that you would do is you would initialize, and you would confirm that it is in a hybrid initialization before pressing initialize, because a standard initialization would not provide us with all the information that we need so easily. Something else that I like to do before starting a calculation is to just check the mesh check, just perform a mesh check to confirm that everything is working. Hang on. My apologies there, I assumed my recording software was paused and I paused it for a second. I have not edited anything without while the screen was off. Okay, so for demonstration, you would then come to your run calculation and you would change the number of iterations from 1. I like to have it at 1,000 so it can have more than enough room to intersect if need be. If it does not intersect as easily, however, conveniently, my data has done within 200 iterations, which didn't take too long on my not very fast PC. Then you would calculate. I'm now demonstrating a secondary calculation because time does allow for it, fortunately. As you can see, it is being calculated the lift and the drag coefficients of the aerofoil, as well as the residuals, and they're all being calculated simultaneously. And once this completes, if time allows, I hope it does. Now I'm thinking about it because I only have 2 minutes left in the recording. What we are waiting for in this stage is for all the lift and the drag to even out to a point where it is would be under normal flow. It is sometimes can take a little while, unfortunately. That is why I had it laid out, and this is the pressure distribution of the aerofoil. I was not expecting this to be available for us right now, so I'll just discuss through this. It's just updating. Thank you very much. This is the pressure distribution, where the blue is the low pressure, which would of course provide us with lift, and the red is the high pressure, which would of course provide us with drag. The green is just the ambient air pressure around, and as you can see, the blue interchange here, this is caused by the compression of air which is happening because of the two aerofoils compressing into each other, creating an area of low pressure air, which overall increases drag for the aircraft. And this is another visualization of it using airflow arrows, which gives us a very useful technique. It's a very similar graph to the pressure distribution, however, it's a more visual of where the air is flowing. As you can see, there's a lot of slower air here,